Matcom tutorials, an investment in knowledge pays the best interest.
Hi guys, you're welcome to my YouTube channel, Matcom Tutorials. If you are new to this channel, please subscribe to my channel, turn on the notification bell icon so that you get notified anytime I post a new tutorial. Today we are going to look at Physics paper 0625/61, that is alternative to practical paper 6, variant 1 of October-November 2020. Now the first question here, let's look at the question. A student determines the density of a modeling clay by two methods. Method 1, A, figure 1.1 shows one face of a piece of modeling clay that the student uses. This is sample A. You can see the modeling clay as shown in the diagram there. Now the student measures the depth D of sample A. Measuring the depth D, the student got 3.2 cm. The first question there is measure and record the length L and the width W of the sample A of modeling clay. Figure 1.1 is drawn to actual size. So if you look at this figure, I have measured it. I got L to be 3.1 cm and I got my W to be 2.7 cm. This is a very simple thing. All you need to do is to just place your ruler across and get the measurement. You can place your ruler across here and get the measurement. You are given centimeters, so you should leave your measurement in centimeters. Now, 2, calculate the volume VA of sample A using the equation VA equals L times W times D. You've been given L as 3.1, you've been given W as 2, you got L as 3.1, got W as 2.7, and you were given 3.2 as your D. So all you need to do is to multiply everything, and that gave me 26.784, and I approximated it to 26.78, leaving it in 2 decimal places. I think that's very cool. That's right. I like leaving in 2 decimal places, and I will also advise you to do so. So figure 1.2 shows sample A on a balance. Record the mass MA of sample A to the nearest gram. We got 50 here. You have 50.78 here. Now to the nearest gram, if we are clearing these decimal points, this 8 comes here and makes this one 8. Since it is more than 4, you have to round it up to 1 and add it to 50. That gives us 51. So let's go to the next question. Method, okay, let's look at this. There's a question here. Calculate the density rho A of sample A of modeling clay using the equation rho A equals MA divided by VA. Give your answer to a suitable number of significant figures for this method and include the unit. You've been told to give your answer to a suitable number of significant figure and then include the unit. Let's look at the values of MA and VA from the previous question. MA and VA. MA, this is MA 51, MA 51. VA 26.78, 51, 26.78, MA 51, 26.78. So our density will be 51 divided by 26.78. This is 26.78. Okay. Well, if you actually used 26.784 in the previous question, you are going to get another answer. Here I got 1.9, 1.9 as my answer. You have to include the unit. So this is gram, and this is cm cube, cm raised to power 3. So the unit is going to be gram per cm raised to the power of 3. Let me rewrite this, my gram. Sorry about that. gram per cm raised to the power of 3. So we have a gram per cm raised to the power of 3. So with that, you have your 2 marks. Let's go to the next one. The student records the volume V1 as 150. He carefully lowers sample B of the same modeling clay into the measuring cylinder until it is completely covered with water. He records the new reading V2 of the water level in the measuring cylinder, and V2 is 182 cm cube. Now calculate the value VB of sample B using the equation VB is V2 minus V1. This is very straightforward. V2 is 182, V1 is 150. So when you deduct 150 from 182, that gives you 32. Let's check the next question. The student measures the mass MB of the sample B. MB is 60 grams. Calculate the density of sample B using the equation density rho B is MB divided by VB. MB divided by VB, that's how you are going to calculate the density. What's the value of MB? MB is 60 and VB is 32. So it's a simple calculation, is 60 divided by 32. And what's the answer? 60 divided by 32, we have 1.88. 1.88. And the question is, give your answer to a suitable number of significant figures for this method and include your unit. What is the unit of density? The unit of density is gram here on top, and then this 32 is in cm cube, so we have cm raised to the power of 3. Okay, let's move ahead. A student suggests that the density of a modeling clay is not affected by the mass or the volume of the sample used. State whether your results agree with this suggestion. Justify your answer by reference to your results. Okay, let's see. Let's see whether what the student said was right. The student suggested that the density is not affected by the mass or the volume of the material. Let's look at our results. Let's look at our results. This one is giving us 1.88 as density, and the second one, let me change this to red. The second one is giving us 1.9, and this one is giving us 1.88. 1.88. Do we really have much difference? 1.88 can actually be approximated to 1.9. So I will agree with the students. For the statement, I will agree with the student. Yes, the student is right. So I can say yes. I can say yes. Yes, because the question is state whether your results agree with the suggestion. Yes, yes. My result actually agrees very well with the suggestion. Yes. Now, how do we show? Justify your answer by reference. Now, how do we reference it? When you look at let me put a text box here. Why is it not responding? Okay. Text. Okay. Now, we want to look at the justification. 1.88 is very close to 1.9. So, I can say answers are so close to each other. So, it is still within the limits of experimental accuracy. Yeah, the answers are so close to each other, so we can actually say they are the same. So it is still within the limit of experimental accuracy. Let me place this one very well so that it fits into the space. So it is still within the limit of experimental accuracy. That's our justification, and then you get your 2 marks there. The next question. Tick the boxes that describe the correct line of sight for taking a reading of the volume of water in a measuring cylinder. Figure 1.3 shows the curved surface of water, which is called the meniscus. So how do you read? Whenever you want to take any reading, you must place your eye perpendicular to what you are reading here, and then it must be at the bottom of the meniscus. The bottom of the meniscus. Bottom of the meniscus. Let's check what they have there. Perpendicular to the scale, yes, it should be perpendicular to the scale. That one is right. Let's see whether there is any other one there. Vertical to the scale, no. Parallel to the scale, along the scale, no. In line with the bottom of the meniscus, that is correct. In line with the bottom. Let's see. In line with the top, no. In line with midway, no, 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 no. So all these are wrong. So you need to tick the 2 boxes and then you get your marks. Now the thermometer in figure 2. Let's see. There's a question on top. Okay. A student investigates the cooling of water under different conditions. Figure 2.1 shows the apparatus she uses. You can see the apparatus here. The thermometer in figure 2.2 shows the room temperature theta R at the beginning of the experiment. Record theta R. Let's see what the thermometer is reading. We have 20 here, so this is 21. This is 21, so we have 21 degree Celsius. That is the reading. Let's go to the next question. Now the next question states that the student pours 200 cm cube of hot water into the beaker. She records the temperature theta of the hot water at time t equals 0. She immediately starts a stop clock. After 180 seconds, she measures the temperature theta shown on the thermometer. Her temperature readings are shown in table 2.1. Now the question is, complete the time column and the column headings in table 2.1. We were told that she used time 0 and also time 180 and also time 180. To complete the heading, this is in seconds and this is in degrees Celsius. Make sure the sign of your degree is on top of C so that you get your complete mark. Complete the time column. I'm reading this. Complete the time column and okay. Calculate the drop in temperature. Calculate the drop in temperature delta theta 1 between time t equals 0 and t equals 180. The drop in temperature between these two times, that is 85 minus 69, and that gives us 16. 85 minus 69, that gives us 16 degrees Celsius. That is the answer. Calculate the average rate of cooling R1 of the water using the equation. R1 is delta theta 1, that is this, that is this, divided by delta T, okay, divided by delta T, where delta T is 180. So that means we have 16 divided by 180. 16 divided by 180. Let's see what's going to give us. 16 divided by 180 is 0. 0. The dot is not really showing. Let me make it bigger. Okay, it's a dot here. Dot. Okay, 0.089. 0.8 and 9. I've done this to two significant figures. That is 1, 2. You may also leave it into two decimal places. That's 0.09. Now, what is our unit? This one is temperature. That's degree Celsius. Degree Celsius divided by seconds. That is the unit. Let's go to the next question. The student empties the beaker. She pours 150 cm cube of hot water into the beaker. She adds 50 centimeters cube of cold water to the beaker. She repeats the timing and temperature recording procedure described in B. The temperature readings are shown. Complete, okay, it's still the same thing. Complete the time column and the heading. So this is seconds and this is degrees Celsius, and this is 0. This is 0, and this is 180. 180. So what's the next thing? We've completed it. Now calculate the drop in temperature. The same thing we calculated. So we have 69 minus 57. 69 minus 5, 7, and that will give us 12. That will give us 12. 12. 69 minus 57. That will give us 12. Okay. Let's go to the next one. That will give us 12. Next question. Now, calculate the average rate of cooling R2 of the water using the equation R2 equals delta theta 2 divided by delta T. Let's get the values. Delta 2 divided by delta T. Let's get the values. Okay. This change in temperature 2 is 12. Change in temperature 2 is 12. Let's see. This one is 12. 12 divided by this one, delta T. Let's see. What is the value? What's the value? What's the value? What's the value? Okay. All right, that's 180. 180. So divided by 180. 180, and our answer is 0.067. Okay, I need to include my units. Degrees Celsius per second. Let me write this properly. Degrees Celsius per second. Okay, what's next now? A student suggests that the average rate of cooling R of the water depends on the difference D between the temperature of water at time t equals 0 and room temperature. Calculate the difference D1 using the readings in table 2.1 and your answer to A. Okay, and your answer to A. Let's look at the value. D should be the difference between the temperature of water at time t equals 0 and the room temperature. Okay. We got our room temperature to be 21 degrees Celsius. Room temperature 21 degrees Celsius. For the first one, R1, where is R1? Okay. For R1 at time t, this is 85. And we got our room temperature to be 21. So for this place, we are going to have, sorry, let me take it to the question. Sorry, okay. D1 is going to be 85. 85 minus 21. 21 is the room temperature, and then 85 is the temperature of water at time t equals 0 for the first one. So this gives us 64. Sorry, this gives us 64 degrees Celsius, 64 degrees Celsius. The second one, calculate difference D2 using your readings in table 2.2. We know our room temperature to be 21. So let's go and look at the temperature at time t equals 0 for the second one. Temperature at time t equals 0 for the second one is 69. 69. So that's what we are going to use. 69 minus 21. 69 minus 21, that is 48. 48 degrees Celsius. Next question. Write a conclusion about the relationship between R and D. Justify your answer with reference to the result. Now, the student actually suggested that the rate of cooling R of the water depends on D. Let's look at it. Let's go and look at R1. D1 is 64. R1 is 0.089. 64, 0.089. Let's look at 48 and R2. 48 and R2. Where is our R2? Where is our R2? 0.067. 0.067. Remember, R1 here, let me write it here. R1 here is 0. Let me use another pen color. R1 here is 0. 0.0, okay, let's just call it 0.9, and R2 is 0. Let's just say 0.7 just to make our comparison. 0.07. What is the relationship now? I can see that for higher value of D1, R1 is 0.09. For a lower value of D2, R2 is 0.07. That means as D decreases, R also decreases. So it means as D increases, R increases. So they are actually proportional. So R depends on D. So I'll write my conclusion now. Sorry. R, rate of cooling R is directly proportional to D. Is directly proportional to D. This means R depends on D. R depends on D. But let me see whether it can take the whole. It means R depends on D. Okay. The second one. Justification now. When R1 equals let me use the word with R1 equals 0.089. If R1 equals 0.089, D1 equals 63. D1 equals 63. That's 63. Sorry, 64. That's 64 degrees Celsius. And let me make it bigger. Let me extend it. For okay, and with R2 equals 0.067, D2 equals 48. D2 equals 48. Therefore, sorry, let me bring it here. Aha. Therefore, as D increases, R also increases. Yeah. Yes, I think this should be enough justification for us. Therefore, let me see. Okay, I'll bring it here, but let me make this thing smaller a little bit. Okay. All right. So the rate of cooling R is directly proportional to D. R depends on D. With R1 equals this, and then this one, that's I think I should put degrees Celsius there. Let me put a space here so that I'll be able to put degree Celsius. Okay, equals 0.67 degrees Celsius. Sorry. Degrees Celsius. Okay. All right, that answers the question. Then the next one is explain why the thermometer scale should be read at right angles. This is also a very simple one. You take readings at right angle to avoid error due to parallax, to avoid or prevent error due to parallax, or you say parallax error. That was a very simple one. Okay, the next one. Explain why the mixture of hot and cold water should be stirred before taking the temperature reading at the start of the experiment. You need to stir the mixture so that the temperature will be even throughout. So I'll just write to obtain an even, oh, sorry. Don't know what really happened. To obtain an even temperature throughout. That's why you need to stir so that the temperature will be even, to obtain an even temperature throughout. Okay, that solves the question. And so let's go to the next one.